In the pursuit of space exploration, not every rocket launch goes according to plan. From technical malfunctions to unexpected events, the journey to the cosmos is fraught with challenges. Join me for today's video. We're going to delve into the fascinating yet sometimes perilous world of space exploration. Here are 15 rocket launches that went wrong. Number 15. SpaceX Falcon 9. Early on September 1st of 2016, a dramatic explosion shattered the tranquility of a Florida launch pad, obliterating a SpaceX Falcon 9 rocket and its precious cargo. The Amos-6 communications satellite primed for an imminent mission. The incident unfolded at Space Launch Complex No. 40 in Cape Canaveral Air Force Station, where SpaceX readied the Falcon 9 for a static fire test ahead of a scheduled September 3rd launch. The routine pre-launch procedure turned into a fiery spectacle. SpaceX confirmed the loss of both the Falcon 9 and the Amos-6 payload, emphasizing that no injuries happened. SpaceX came forward saying there was an anomaly on the pad resulting in the loss of the vehicle and its payload. The repercussions rippled across multiple fronts. The blow to the Amos-6 provided a significant setback for its owner, Spacecom, with a pending sale contingent on the satellite's successful launch. Share values of Spacecom plummeted as news of the explosion spread. Facebook, a major user of Amos-6, expressed disappointment, but they remained steadfast in its mission to provide internet access to underserved regions. The incident also did cast a shadow over other companies awaiting these Falcon 9 launches, notably Iridium. The planned launch of its next-generation satellites faced delays as investigations into the explosion unfolded. SpaceX, amidst a busy launch schedule, now navigated a challenging end-of-year manifest, impacting its commitments to various customers. Number 14. Soyuz MS-10. The Soyuz MS-10 mission was a Russian crewed spaceflight intended to transport cosmonaut Alexei Ovchinin and astronaut Nick Hague to the International Space Station. Now, the launch was scheduled for October 11, 2018 from the Baikonur Cosmodrome in Kazakhstan, with high anticipation. However, just minutes after liftoff, the mission took a harrowing turn. As the Soyuz FG rocket carrying the Soyuz MS-10 spacecraft ascended, a critical failure happened during the separation of the rocket's first and second stages. The escape system was triggered, jettisoning the crew module away from the rocket. The launch escape system, designed to rapidly propel the crew away from the rocket in the event of an emergency, successfully activated, demonstrating its crucial role in ensuring astronaut safety. The spacecraft's descent involved a ballistic trajectory, subjecting the crew to higher G-forces than a standard landing. Both Ovchinin and Hague emerged from the capsule unharmed, but they were shaken. The investigation that followed delved into the cause of the rocket failure. It was determined that a sensor was damaged during the rocket's assembly at the Baikonur Cosmodrome. This sensor's improper installation led to the first and second stages of the rocket failing to separate correctly. This anomaly triggered the launch escape system, a life-saving mechanism that averted a potential disaster. Number 13. Zenit 3SL. The Zenit 3SL, a launch vehicle developed by the Ukrainian company Uzunoi Design Offices and manufactured by Uzmosh, was initially designed as part of the Sea Launch Project, a collaborative effort involving Russian, Ukrainian, American, and Norwegian contributions. The purpose of the Zenit 3SL was to provide commercial satellite launches into geostationary orbit using a floating platform in the equatorial Pacific Ocean. Now, it was constructed with a two-stage design. It featured a Zenit 2S rocket as its first stage, powered by a modified RD-171 engine. The second stage utilized a block DMSL and an RD-120 engine. Now, these engines were known for their reliability and their power, with the RD-171 being one of the most potent liquid rocket engines ever built, capable of generating over 800,000 pounds of thrust. However, despite the initial promise of it, the project faced a series of setbacks and failures. The launch history was marred by notable incidents, including mission anomalies and outright failures. One such failure happened in 2004, when a Zenit 3SL rocket carrying the NSS-8 satellite veered off course, resulting in the loss of the payload. The failures of the Zenit 3SL were attributed to a combination of technical issues, manufacturing challenges, and the complexities of coordinating international collaboration. The Sea Launch platform had faced financial difficulties, leading to a hiatus in launches and a subsequent bankruptcy filing in 2009. The economic and geopolitical landscape contributed to the discontinuation of this project. Now, its troubled track record, coupled with the evolving landscape of commercial satellite launches, led to a diminishing demand for the rocket. The space industry's shift towards newer, more cost-effective launch vehicles such as SpaceX Falcon 9 further marginalized the Zenit 3SL. Number 12. The Titan 4B. The Titan IV-B, part of the Titan rocket family, was a launch vehicle developed by the United States. It was built by what is now Lockheed Martin. This played a crucial role in supporting a variety of military and government missions. The development of the Titan IV-B aimed to meet the evolving needs of the United States Air Force and other government agencies for launching heavy payloads into space. With a unique design, it featured a two-stage configuration. The first stage was powered by a pair of large, solid rocket motors, augmenting the thrust provided by the liquid rocket engines. The second stage was a liquid rocket engine for propulsion, and the combination of these technologies resulted in a launch vehicle capable of carrying heavy payloads into a variety of orbits, including geostationary and polar orbits. The Titan IV-B was notable for its substantial capacity, capable of lifting large reconnaissance satellites, communication satellites, and interplanetary probes. Its powerful Centaur upper stage, equipped with an RL-10 engine, further expanded its versatility, allowing for precise orbital insertions. Now, despite its capabilities, the Titan IV-B program faced some challenges and setbacks during its operational history. One significant incident happened in 1998, when a Titan IV-B carrying a classified payload experienced a launch failure. The investigation revealed a problem with the guidance system, leading to the destruction of the rocket and its payload. It's faced increasing competition since then from more cost-effective and versatile launch vehicles such as the Delta IV and Atlas V, which utilized newer technologies and benefited from advancements in the commercial space industry. As a result, the Titan IV-B program was eventually phased out, with its last launch happening in 2005. Number 11. The Atlas Centaur AC-67. Another one developed by Lockheed Martin, the Atlas Centaur AC-67 was part of the Atlas Centaur family of rockets, known for their reliability. This variant was particularly notable for its use in launching a variety of payloads, including communication satellites, scientific instruments, and interplanetary probes. It was built on the foundation of the Atlas rocket as its first stage and the Centaur upper stage. The Atlas Centaur AC-67 boasted a two-stage configuration. This combination allowed the rocket to achieve precise and flexible orbital insertions, making it suitable for a wide range of missions. It also contributed significantly to the success of various space missions, earning a reputation for its reliability and efficiency. It played a crucial role in launching satellites into geostationary orbits, supporting scientific endeavors and enabling interplanetary exploration. One of its notable missions was the launch of the Voyager probes, which provided invaluable data about the outer planets of our solar system. However, the Atlas Centaur AC-67 program also experienced some challenges. Notably, in 1986, an AC-67 rocket carrying Navy communications satellite experienced a launch failure. Approximately 49 seconds after liftoff, the vehicle began experiencing erratic pitch motions. Moments later, at T+54 seconds, the range safety officer issued the destruct command due to the abnormal flight behavior. The rocket was destroyed, resulting in the loss of the payload. Subsequent investigations into this failure revealed that the root cause was a malfunction in the guidance system, specifically the Inertial Navigation Unit, or the INU, responsible for providing guidance and navigation data to the rocket's control system. That experienced an anomaly. The INU erroneously interpreted normal pitch program data as excessive, leading to the generation of incorrect steering commands. Number 10. Vega Flight VV-17. The Vega flight launched on November 16, 2020, encountered a critical failure during its ascent. The mission aimed to deploy two Earth observation satellites, Ceostat Ingenio for the Spanish government and Taranis for the French space agency CNES. Operated by Ariane Space, the Vega rocket lifted off from the Kourou spaceport in French Guiana. The launch proceeded nominally until approximately 8 minutes after liftoff, during the second stage ignition phase. At this critical juncture, the Vega rocket encountered a deviation from its intended trajectory. The anomaly manifested as an issue with the altitude control system of the Zefiro 23 second stage motor, a solid rocket motor designed to propel the Vega's second stage. The thrust vector control subsystem responsible for steering the motor experienced a malfunction, resulting in an incorrect orientation of the rocket. The nozzle which directs the exhaust plume and controls the rocket's altitude deviated from the planned position. Now, this deviation led to a loss of control over the rocket's orientation, preventing the successful continuation of the mission. As a consequence of that control system anomaly, the Vega rocket was unable to deliver the satellites into their intended orbits. The mission was officially declared a failure, marking a significant setback for Ariane Space and the European space industry. The subsequent investigation focused on identifying the root cause of this failure. The examination revealed that a flaw in the thrust vector control subsystem, likely related to the manufacture or assembly process, led to the incorrect positioning of the rocket's nozzle. This deviation from this planned trajectory triggered an automatic destruct mechanism, ensuring the safety of the mission by preventing an uncontrolled rocket trajectory. In response to those findings, Arianespace implemented corrective actions to address the specific issue within the control system. Now, this incident emphasized the meticulous engineering and quality control required in the aerospace industry, especially when dealing with critical components of launch vehicles. Number 9. The Atlas Able. In 1958, the Atlas Able rocket was strapped with a combination of the Atlas LV-3 missile, the first stage of the rocket, and the Able upper stage, powered by a rocket engine. The goal was to propel the Pioneer 1 probe beyond Earth's atmosphere and towards the Moon. However, the mission encountered a series of challenges that ultimately led to a failure in the early days of the space race. The launch took place at Cape Canaveral Air Force Station in Florida. Almost immediately after liftoff, the rocket experienced difficulties. The Atlas first stage performed adequately, lifting the vehicle off the pad, but trouble arose during the transition to the Able upper stage. An anomaly happened in the guidance control system, causing the rocket to deviate from its trajectory. About 77 seconds into the flight, the range safety officer made the critical decision to terminate the mission by issuing the destruct command. The destruction of the rocket happened at an altitude of about 9 miles, resulting in a cloud of debris falling into the Atlantic. The investigation into the failure revealed that the guidance system malfunctioned due to a malfunctioning amplifier. This caused incorrect signals to be sent to the rocket's engines, leading to a loss of control. The decision to destroy the rocket was made to prevent it from veering off course and posing a threat to populated areas. While the Atlas Able failure was a setback, it provided valuable insights into the complexities of space exploration. Engineers and scientists, they learned important lessons from this incident, contributing to subsequent improvements in rocket design. Despite this failure, the Pioneer 1 program continued, eventually achieving success with subsequent missions. Pioneer 1's primary objectives were to study cosmic rays, solar wind and magnetic fields, and lunar radiation. And while it didn't achieve a lunar impact, it provided valuable data that contributed to our understanding of space, and it paved the way for future lunar exploration missions. Number 8. Vanguard TV3. The Vanguard TV3 launched on December 6, 1957. It was a historic attempt by the United States to place its first artificial satellite into orbit. Operated by the Naval Research Laboratory and part of Project Vanguard, it aimed to usher in the country's entry into the burgeoning space race. However, the mission quickly turned into a memorable episode, earning it the nickname Flopnik. It consisted of a small aluminum sphere measuring about 6.5 inches in diameter and weighing less than 4 pounds. Equipped with 2 transmitters, this teeny satellite transmitted engineering and telemetry data using a 10-milliwatt 108 MHz transmitter. On December 6, 1957, at 16:44 hours, the launch from the Atlantic Missile Range in Cape Canaveral initiated as planned. However, approximately 2 seconds after liftoff, the rocket lost thrust and descended back to the launch pad, leading to a fuel tank rupture and subsequent explosion. The Vanguard satellite, thrown clear during the incident, landed a short distance away, still emitting a beacon signal. Now, despite the damage, the satellite's remnants are now displayed at the Smithsonian Air and Space Museum. The exact cause of the failure was not definitively determined due to limited telemetry information during that early phase. Martin Maricetta suggested that a low fuel tank pressure allowed burning fuel to leak into the fuel system. In contrast, General Electric posited a loose fuel connection, which in hindsight appeared connected to the initial problem. The investigation indicated lower than nominal tank and fuel system pressures, which led to insufficient pressure in the injector head. Now, this resulted in a pressure spike, burning through the injector rings and causing combustion chamber ruptures. A shock wave in the booster's thrust section ruptured a fuel feed line at T+1 seconds, halting the engine thrust. Subsequent modifications, including increased tank pressure and the use of ethane gases, addressed those issues, ensuring that the X-405's engine's reliability in subsequent launches and static firing tests. Moving on to number 7, the Antares A1. In a dramatic turn of events, an Antares rocket on a mission to supply the International Space Station erupted into a massive explosion just 6 seconds after liftoff. This catastrophic anomaly, witnessed on October 28, 2014, marked a pivotal failure for Orbital Sciences Corporation's commercial spaceflight aspirations. Loaded with supplies and scientific experiments, the Signis spacecraft atop the Antares rocket was meant to contribute to NASA's commercial resupply services for the ISS. Now, the critical decision-making moment unfolded when safety officers, vigilant for any of 10 specified problems during liftoff, initiated the flight termination system, triggering the rocket's destruction. This subsequent explosion, visible for miles along the coast, illuminated the sky, but crucially adhered to the established safety protocols, ensuring that no injuries happened. The Antares 1 failure underscored an inherent complexity and risk associated with space exploration. This ordeal unfolded in front of thousands of onlookers near the Wallops Island on Virginia's eastern shore, turning what was anticipated as routine launch into an unexpected disaster. The investigation into this failure pointed to a malfunction in one of the engines, leading to the loss of thrust and the rocket's descent. The launch's aftermath prompted a briefing at the Visitor Center, where NASA and orbital sciences executives acknowledged the challenges of spaceflight. William Gerstenmaier from NASA emphasized the difficulty of the business and the need to reorganize its demanding nature. Frank Culbertson of Orbital Sciences acknowledged the loss of the hardware but emphasized the absence of human casualties. The incident served as a reminder that spaceflight is neither routine nor simple, renewing respect for the cautionary principles that guide the industry amid the audacious pursuit of maintaining a human presence in space. Number 6. The Ariane 5 Flight 501. Ariane 5 Flight 501 launched on June 4, 1996, only to end in a catastrophic failure for the European Space Agency's Ariane program. The Ariane 5 was designed to be a reliable workhorse, known for its successful predecessors, but this mission took an unforeseen turn. The Ariane 5 program had a successful track record, with numerous launches preceding Flight 501. The rocket was designed to carry a variety of payloads into orbit, and its reputation for dependability was well established. But not today. The timeline for Flight 501 began as routine. The payload included the Cluster mission, consisting of 4 scientific satellites intended to study Earth's magnetosphere. Additionally, the payload featured the Spot 4 Earth observation satellite. The mission aimed to deliver these satellites into geostationary orbit. The Ariane 5 was equipped with 2 solid rocket boosters for the initial ascent. However, just 37 seconds into the flight, disaster struck. The rocket experienced an abrupt deviation from its intended trajectory, leading to a self-destruct command. The failure was as swift as it was bad. The rocket disintegrated in mid-air, resulting in a dramatic explosion that scattered debris across the Guiana Space Center in French Guiana. The entire mission lasted less than a minute, a stark departure from the expected success. The root cause of this failure was traced to a software issue in the inertial reference system. The guidance system adapted for the Ariane 4 encountered a rapid conversion of a 64-bit floating point number to a 16-bit signed integer. Now, this numerical conversion error happened during the rocket's ascent. It led to a loss of accurate trajectory information. This software flaw hadn't surfaced during the Ariane 4 missions due to the differences in flight trajectories between the 2 rockets. However, the Ariane 5's trajectory exceeded the limits of the adapted software, triggering this catastrophic failure. Number 5. The Proton M, Briz M. This heavy-lift launch vehicle known as the Proton M is a direct descendant of the Soviet-era Proton and is meticulously crafted by Khrunichev, finding its liftoff stages at the historic Baikonur Cosmodrome in Kazakhstan, specifically from launch sites 81 and 200. The Proton M made its inaugural performance on April 7, 2001, marking the commencement of a series of 112 launches by July 21, 2021. However, like any intricate dance, not all steps have been flawless. Of the 112, 11 launches experienced partial or complete failures, resulting in a success rate of 90%. Now, these hiccups revealed themselves in various forms: 4 due to Proton M glitches, 6 caused by the misbehavior of the Briz M upper stage, and 1 of a consequence of one of the upper stages misfueling, rendering the Proton too hefty for its orbital mission. Possibly the most notable misstep happened in July of 2013 during a Proton M DM-30 mission carrying the GLONASS satellites. It unfolded dramatically as the booster began an unscripted ballet of left and right pitches, resisting the onboard guidance computer's desperate attempts at correction. Within 24 seconds, the upper stages and payload detached, flames erupted, and a mere 6 seconds later, impact with the ground became an irreversible reality. The investigation unveiled a pivotal detail. 3 angular velocity sensors in the first stage, crucial for yaw control, were incorrectly installed. This blunder led to a rocket without effective yaw control, sealing its fate. Telemetry data hinted at yet another anomaly, a premature detachment of a pad umbilical, suggesting an early launch before the engines reached full thrust. The aftermath of this tragedy triggered a seismic shift in Russia's space realm. The July 2013 failure prompted a reorganization of the nation's space industry, birthing the United Rocket and Space Corporation in August of 2013. Deputy Prime Minister Dmitry Rogozin underscored the industry's need for state supervision to navigate its tribulations, emphasizing that, quote, extremely harsh measures would herald the end of Russian space industry as we know it. Number 4. The N1L3 explosion. The N1L3, often hailed as the Soviet Union's lunar dream machine, embarked on a journey that encapsulates the highs and mostly lows of space exploration. Crafted with the ambitious goal of landing cosmonauts on the moon, this behemoth faced a tumultuous series of failures that turned its lunar aspirations into a cosmic tragedy. Picture this, a colossal rocket, the N1, standing proudly on the launch pad, ready to punch through Earth's atmosphere and usher in a new era of lunar exploration. The first act began on February 21, 1969, with the maiden flight of the N1. Anticipation hung thick in the air, only to be shattered seconds later as the rocket succumbed to a cataclysmic failure. 4 out of its 30 engines malfunctioned, sending the colossal rocket into a fiery plunge back to Earth. Undeterred by this initial setback, the Soviet engineers patched up their lunar dreams and aimed for another launch on July 3, 1969. This time, the N1L3 performed a mesmerizing dance on the launch pad, with all 30 engines roaring in unison. Yet just moments into its ascent, tragedy struck again. A ruptured line in the first-stage propulsion system led to a spectacular explosion that left the rocket in ruins. Not one to yield easily, the N1L3 faced its next challenge on June 27, 1971. The third attempt was poised to be the charm, but the cosmos had different plans. A control system malfunctioned during the first stage ascent and led to a violent wobble, forcing the automatic safety system to shut down the engines. The N1L3 once again met its demise in a brilliant display of fireworks. Why did the N1L3 face such a string of failures? Well, the answer lies in the intricacies of its design. The complexity of coordinating 30 engines in the first stage posed a monumental challenge. The engines were arranged in a cluster, an engineering feat that proved difficult to master. The control system struggled to maintain stability, leading to a catastrophic result. As engineers delved into the failures, they discovered a myriad of issues, from problems in the propulsion system to glitches in the control system. The N1L3 became a victim of its own ambitious design. It was trying to push the boundaries of technology at the time. These engines, the heart and soul of the rocket, became its Achilles heel. Number 3. The Signis Orb 3. On the ill-fated night of October 28, 2014, Orbital Sciences geared up for the Orb 3 mission, an ambitious endeavor to deliver cargo to the ISS. The Signis spacecraft, bearing the name SS Deke Slayton in honor of one of NASA's Mercury 7 astronauts, stood poised atop the Antares rocket, ready to soar into the expanse. This marked the first attempt of the Antares 130, featuring a more powerful Castor 30XL second stage, and the swan song for the standard-size Signis pressurized cargo module. The mission held the promise of being the third of 8 flights under the Commercial Resupply Services contract with NASA, showcasing Orbital Sciences' commitment to advancing space exploration. Now, the stage was set for a night of milestones as Orbital Sciences prepared for its inaugural nighttime launch from the Mid-Atlantic Regional Spaceport at Wallops Flight Facility in Wallops Island, Virginia. However, fate had other plans, as the launch scheduled for October 27, 2014, faced a last-minute delay due to safety concerns sparked by a sailboat venturing too close to the exclusion zone. The launch was scheduled for October 28, 2014. The anticipation was palpable as the seconds counted down. Yet just 15 seconds after liftoff, disaster struck. A propulsion failure in the first stage triggered a rapid descent back to the launch pad. The range safety officer engaged the flight termination system in a desperate bid to avert further catastrophe. The resulting explosion sent shockwaves through Maryland, situated 20 miles away. The fire, a manifestation of the mission's demise, was left to burn itself out overnight. An initial telemetry data review found no anomalies until the point of failure, leaving investigators puzzled about the sudden unraveling of the mission. NASA, in a press release, confirmed the loss of the entire payload and significant damage to the launch pad. A swift response saw investigative teams examining the debris at the crash site, while a survey revealed the damage to the launch pad and site fuel tanks. Subsequent investigations honed in on the cause. The LOX turbo pump had exploded, creating a shockwave that damaged propellant lines and sparked a fire. The precise trigger, whether a defective pump bearing or loose debris ingestion, remained elusive. The Orb 3 mission, meant to be a testament to human ingenuity, instead etched itself into history as a poignant reminder of the unpredictable challenges that accompany space exploration. Number 2. The Long March 5. In the grand narrative of space exploration, the Long March 5, a heavyweight champion in the Chinese rocket fleet, had its own moment under the cosmic spotlight. The stage was set for a momentous occasion as the Long March 5, a reliable workhorse developed by the China National Space Administration, stood tall at Wenchang spacecraft launch site. The mission, designated as Tianqiu-1, aimed to showcase the capabilities of the Long March 5, laden with cargo destined for China's Tiangong-2 space station. This launch marked a pivotal step in China's ambitious space station program. The Long March 5 comes in at 200 feet, weighing about 643 pounds, and with a thrust of about 834 tons. The excitement was palpable at launch, and it was scheduled for April 20th of 2017, heralding a new chapter in China's space odyssey. However, fate had a different trajectory in mind. In a twist of cosmic irony, the Long March 5 faced a setback that would resonate through the annals of space history. The launch vehicle, entrusted with the crucial task of propelling China's space aspirations, succumbed to an anomaly. Within moments of liftoff, the Long March 5 encountered a propulsion failure, leading to a cascade of events that resulted in the termination of the mission. The aftermath of the failure echoed through the space community. The meticulously planned mission to resupply the space station met an unexpected demise. As investigations unfolded, the precise cause of the failure emerged. The oxidizer's turbo pump suffered from technical problems, but it would seem as though the entire mission was set for failure from the get-go. Before the rocket even left the launch pad, it already faced a bevy of challenges. Technical hitches like complications with an oxygen vent and engine cooling were identified during the pre-launch operations, leading to an almost 3-hour delay. As the final countdown commenced, it encountered interruptions on 3 occasions, attributed to issues with the flight control computer and tracking software. Number 1. Starship SN1. On February 28, 2020, SpaceX faced a significant setback as the Starship SN1, the second prototype of the Starship launch vehicle, was destroyed during a pressurization test at the Boca Chica, Texas facility. The vehicle burst into flames before completely disintegrating near the bottom. Once the smoke cleared, very little of the Starship survived the test. The destruction was reminiscent of a previous SpaceX incident involving another prototype, Starship Mark 1, during a similar test. Elon Musk, the founder of SpaceX, initially remained silent about the SN1 incident, but later tweeted a video of the test on March 2nd, accompanied by a nonchalant comment asking how everyone else's night was. Musk said that the test failed because they were so laser-focused on the SN2. Odd, indeed. The fate of the Starship SN1 raised some questions about SpaceX's development timeline, as Musk had previously suggested a flight for Starship Mark 1 within 1 or 2 months at a September launch in Boca Chica. Leading up to those pressurization tests, SpaceX appeared to be preparing Starship SN1 for a static fire test, with Musk tweeting yet again about the tank getting ready for Raptor attachment. Plans included a suborbital test flight following the static test, aiming for an altitude of about 12 miles and a subsequent landing back at Boca Chica. However, the incident with the Starship SN1 underscored the challenges in SpaceX's development process, with the company yet to secure a launch license from the Federal Aviation Administration for the suborbital test. But SpaceX has seen literally hundreds of successful launches of their Falcon 9 and Falcon Heavy rockets, so 1 or 2 failures isn't the end of the world for them. Not even close. Plus, when a company is owned by one of the richest people in the world, does a failed launch or 2 even matter? Probably no way. I'll see you guys next time. Thank you to our channel members.